All right. So last class we started this space truss problem, and we started by figuring out the directions. Well, actually, we started with our free body diagram, and then we're coming up with the Cartesian vectors for the directions of these members from C to A and from C to B. So we went through C to A, and then by symmetry, the only difference for C to B was it's in the negative x direction instead of the positive x direction. The y and z components were the same. That should be a root 27. All right, so now from our free body diagram, now we can write our equations of equilibrium. All right, so if we start by looking at the forces in the x direction, of the four forces here, I have 150 pounds, which is only in the negative z direction, FCD, which is only in the negative y direction. So it's these two members here that only have x components. Just scroll up a tiny bit here. So that's going to be 3 over root 72 times FCA, or FAC, FCA doesn't matter, FAC, and then minus 3 over root 72 times FBC. Okay. So what does that tell us? FAC equals FBC, which we probably could have determined by looking at the symmetry of the problem in the first place. So we know FAC equals FBC. All right, now we'll move on to the y direction. So in the y direction, I'm going to have these two components of these two forces, which I'm going to call both of them FAC now, because I know that their magnitudes are the same. So that would be minus 2 times 6 over, so let's make that plus 2, put the negative in here, minus 6 over root 72 FAC, and then nothing for the 150 pounds, but then I also have a minus FCD. Anything else? No. So then I can also express FCD in terms of FAC. So FCD then is equal to negative 12 over root 72 FAC. Oh, not negative. Yes, negative. That's right. So that means either this is in compression or both of these are in compression. My method of staring, you can probably figure out which one it is, or we'll go on to the next equation. Net force in the z direction equals 0. Which members are going to have forces in the z direction? Right, so we've got the 150 pounds, our suspended weight that's in the negative z direction, and these two both had z components, and FCD doesn't, because it's just in the y direction. So we write minus 150 pounds, and then because we have two of them, minus 2 root 27 over root 72 times FAC. And that's it. So we can solve for FAC. And it looks like it's going to be negative 150 pounds over 2 times root 72 over 27. Okay, so negative 122.5, because we drew it as if it was tension and it came out negative, and that's pounds. We know that's going to be a compressive force. And we also know that's going to be FBC because they're the same. Okay, and from this, we go back up to here and we can solve for FCD. So negative 12 over root 72 times negative 122.5. 173 pounds. And it's positive, so that means that one's going to be in tension. All right, so we found the forces of those three. Let's just highlight them. So this one was in tension. These two were both in compression. So there's still three members of the space truss. Which point should we go to next? Okay, so we would go to A, B. Why would we go to A, B, and not D?
D has the FX of 5 and 7 reaction.
Right, I actually have 5 unknowns at D. I have 3 components of reaction, and then I have these 2 tension or compression. At A, I actually have 4 unknowns, because I'm going to have an X and a Y reaction, and I'm going to have AB and AD. So A wouldn't be a good choice either. The best choice would be B, because B has 3 unknowns. It only has a Y reaction force, and then it has tension in AB and in BD. So that would be the point we should go to next. I mean, we could do A, but we just can't solve it. So we then need to go to another point to get a bigger system of equations, which is going to be more challenging to solve without making a arithmetic error. So it'd probably be better to go to B. So that's what we'll do. Free body diagram of B. All right, so B, now we're going to do this. And we're going to take a picture. Okay, so I'm just going to copy this onto the next page so we got it for reference. Then I'll erase it when we're done. So if we have our point B here, the forces acting on B are going to be FBC, which we know is in compression already. So it's in compression. We'll draw it in. Oops. I'll draw it in going down towards B. And then I've got FAB. Don't know if it's tension or compression, so I'm going to assume it's in tension. And FBD, again, I don't know if it's tension or compression, so we'll assume it's in tension. And then we have the reaction force with the wall, which is going to be in the Y direction. And I don't know whether it's going to be in the positive Y direction or the negative Y direction, so it doesn't really matter. I'm going to assume it's in the positive Y. So let's label those. So this is FBC, which was 122.5 pounds. Compression. And this one's FBD. And this one's FAB. And this is my reaction. Let's just call that BY. Okay. So BY is going to be in the Y direction, so we'll just multiply that by J hat to turn it into a vector. BC is going to be the 122.5 or negative 122.5 times the unit vector we had before. Actually, let's not clutter up the free body diagram. Let's bring those vectors in. We'll write them underneath. All right. So what's the direction of FBC? That's going to be the opposite of this direction, because this assumed we were in tension. So it's going to be positive. Oh, I can see College of the Rockies now. Can you guys see me now? All right. So 3 over root 72 I hat plus 6 over root 72 J hat plus root 27 over root 72 K hat. All right. The other one we need the direction of is this one, so FBD. So BD is actually in the XZ plane. So if we're going from B towards D, how far are we going along the x-axis? Plus 3 feet. So the positive x-axis is this way. So that would be 3 I hat And then it's going to be 0 j hat because it's not moving in the y direction. And in the z direction, it's going to be plus root 27 k hat. And I want to divide by the modulus of that, so that would be root 27 squared, which would be 27, plus root 3 squared, which would be 9, 27 and 9, 36, square root, makes that 1/2, and root 27 over 36, which is the same as, oh, over 6, yeah, sorry, root 36. If we take a 9 out of that, it becomes root 3 over 2. Root 3 over 2. Right, because it's just a 30, 60, 90 triangle. All right. FAB is along the x-axis. BY is along the y-axis. Don't need to write their directions. So we can go to equations of equilibrium. Can't seem to write this morning. Equations. So our first equation of equilibrium, I can do them in any order, but if we do the x, what have I got in the x direction? I have FAB, which is going to be in the positive x direction. So that would be AB. I have BC as being positive here, but that should be negative. BC. That's compressive. That has to be negative. Let's get back over here. Oh, right. It's going to be everything negative. Yep, you're right. Because it's the opposite direction, but it's on the other. So all of these are negative. Absolutely. Sorry about that. So FAB minus 3 over root 72 FBC, or FBC we know, and 22.5. And then plus 1/2 FBB. Anything else? Okay, so we've got 2 of our 3 unknowns in that equation. What about the y direction? I have BY for sure. And then a component of FBC, so minus 6 over root 72 times 122.5 pounds. Anything else? Nope. So that's going to give me my answer for BY, which I don't really, it's not one of the truss members, but Z 0. All right, in the Z direction, we've got what? Components of FBC and FBD. So the component of FBC is going to be minus root 27 over 72. times 122.5 pounds. And then of FBD is going to be plus 3 over 2 BD. All right, so that's only got one of our unknowns. That's only got one of our unknowns. That one's got two of our unknowns. So we'll solve these two and then substitute into this one to solve for FAB. $86.6, and is that going to be positive or negative? Positive. 86.6 pounds. So in the direction we assumed, which was the positive y-axis. Oh, sorry, not the positive y-axis. That one's just in tension. Sorry, was that FBD you gave me, or was that BY you gave me? It's both. Is BY positive or negative? It's positive as well. And then, oops. Solve this one for FAB. FAB equals 0. All right, so let's put those in on our diagrams. FBD, oops, highlight those first. All right, so we had FBD was in tension, and FAB was zero force member. So the only one that we have left is FAD to finish the truss. Anyone like to make a guess or make an argument for not doing equations of equilibrium?
Symmetry is the same as for the EKD.
Right. By symmetry, it's going to be the same. Same as dB. So just make a note of that. Symmetry. And that would be F AD equals FBD BD. Yeah, I said BD. My pen's just not listening to me. Equals 86.6 pounds tension. I'm going to go back up here and draw that in as complete as well. Oops. So we had 3 tension, 2 compression, and 1 zero force member. All right, and that one was fairly easy because it was really just one tetrahedron that we were solving. We had different reaction forces on the ends, but It was the simplest space truss that you could possibly draw. The next problem is going to be a little bit more challenging. So this is some kind of looks like some kind of a communications tower. And it's got both a vertical and horizontal force on the point G, and it's going to have reaction at points A, B, and C. What's the nature of the reaction at B? Right. There's a two-force member here that's connected to the space truss here, which is only vertical. So it's only going to have a z-axis component of reaction at B. What about at A? Scroll down so you can see the other axes. A would have an X and Z component, and then C is a ball and socket joint. So it would have X, Y, and Z components. So we have total of 6 reaction forces, which would mean it should be fully constrained. All right, we're not going to start here though. We're not going to have to solve for any of the reaction forces. What we're supposed to do is determine the force in members GD, GE, and FD of the space truss and state if the members are in tension or compression. So we don't have to solve the whole thing. We're going to be looking for GD, GE, and FD. So what kind of a strategy would we have to find those 3 members?
We could find all the reactions at G or components at G and F.
Right, so we could use method of joints at G and then at F, and that would cover all of the ones that we need. Or we could use a method of sections. Right? We could cut a section that goes through these 3 that we're looking for, and then plus EF and FC. That would also work. I think it's probably going to be easier to use method of joints than the method of sections. It's a 3-dimensional problem like this, since there's only two joints we'd have to do anyway. So let's do that then. So method of joints at G. So we'd start at G because that's the only place we have known forces, and I have 3 unknowns. So I'll be able to solve for those. And then to find this member DF, I could go to D or to F. F would be way easier. F would then have 3 unknowns because this would now be a known force. And if I went to D, I would still have 1, 2, 3, 4, 5 unknown forces. So I couldn't do it. I couldn't do D without also doing E or F. So we would go to F afterwards. All right. So in order to use the method of joints on G, we're going to need to have the direction of these Cartesian vectors. So I'm going to need the direction of GD, GE, and GF. So that would be U, G, D. So the unit vector in the direction of GD. This is actually going to be easier because G is on the z-axis. If instead of going from G to D, if we continue all the way down from G to A, that's going to be the same direction. It's just a longer vector, but we're going to turn it into a unit vector anyway. So if we go from G to A, how far have we gone on the x-axis? That would be plus 2 feet. I'm just writing equals U, G, A. So it'd be 2 I hat. And how far have we gone on the y-axis? Okay, so that's 3 feet in the negative y direction, so minus 3 j hat. And how far have we gone in the z direction from G to A? Minus 12 feet. Okay, and then to convert that into a unit vector, we would divide by its length. So 12 squared is 144 plus 9 plus 4. Yeah. All right, so there's that unit vector. We also need unit vector from G to E, which is going to be the same as the unit vector from G to B. Okay, same direction. So from G to B, how far do we go in the x direction? Right, basically, by symmetry, the only thing that's going to be different is this one's going to be in the positive y-axis. So it'd be 2 over root 157 I hat plus 3 over 157 root 157 j hat minus 12 over root 157 k hat. All right, and the last one, unit vector from G to F, which is the same as the unit vector from G to C. All right, so if we're looking from G to C, how far do we go in the x-axis, in the x direction? Minus 4 I hat. How far do we go in the y direction? Right, this is in line with B. B and C are parallel to the y-axis, so that'd be plus 3 feet in the j, or in the y direction, and then it's still going to be minus 12. This one's a different length. This member is longer than the other two. So it'll be 144 plus 16 should be 169. So root 169 would be 13. All right. So with those Cartesian direction vectors, now we can move on to free body diagram and equations of equilibrium at G. Okay, so G we know has two external forces on it. One along the z-axis, that's negative 500 k hat pounds, and this one's going to be 200 j hat pounds. And then we have the forces in the three members. Do you think they're going to be in tension or compression? Or a little bit of both? Both. So we could either make a guess as to which ones are going to be in compression and which ones are going to be in tension, or we can just draw the diagram as if they're all in tension. And when we get a negative answer, that indicates compression. There's not a right or wrong way of doing this. There's just two different conventions. I kind of like to think about the answers before I solve them and anticipate which ones are going to be in compression, but at the same time, I like to stick with a convention so that when I get the negative answer, that always means compression. So even though I'm pretty sure that GE and GF are both going to be in compression, and GD might be in tension, but it might also be in compression. I'm going to draw them all in as tension. And I'm going to expect at least two of them are going to be negative. They're going to be compression. If you want to draw them in as compression, the ones that you think are going to be compression, absolutely fine. The only thing that you need to remember is when you get a negative answer, it's the opposite of what you assumed. It doesn't always mean compression unless you always assume tension. That's where it gets a little bit safer to always assume the same thing, even when you know it's wrong. So that's FGD, FGF, and the last one is FGE. All right, so I've got three unknowns. Should be able to solve my equations of equilibrium. All right, which one do you want to start with? Not X? Okay. We're going to have to write all three of them anyway, but we can start with one of the ones that we have a known force for and hope that we can solve it. The difficulty is that all of my unknowns have X, Y, and Z coordinates, which means we're going to end up with a system of three equations and three unknowns that we can't easily simplify. So you said you don't want to start with X. Which one would you like to start with?
Y.
Net force Y equals 0. So I know I've got this 200-pound external force on the top in the Y direction, so 200. And then each of the forces are going to have Y components. So the Y component of this one is going to be negative 3 over root 157. That's going to be FGD. And then I got plus 3 over root 157 FGE. And then the last one is plus 3 over 13 FGF. All right. Again, it doesn't really matter what order we put these in. If I do the Z direction next, it has the negative 500. And it's going to have the Z components of each of the others. So 12 over root 157. FGD minus 12 over root 157 FGE minus 12 over 13 FGF. And then we can do X. X has no constant term. So it's just going to have the X components. So that's 2 over root 157 for the first two. 2 over root 157 FGD plus 2 over root 157 FGE minus 4 over 13 FGF. I've got 3 equations. Each equation has 3 unknowns. What would be a good strategy for solving? I think we're going to have to use a matrix. So before we set up the matrix, there's lots of ugly coefficients in here. So what I'd like to do is, before I put them into the matrix, multiply each equation by some number that's going to give me a leading number that, if it's not 1, at least it's a whole number. So what should I multiply this first equation by? I think I'd multiply by root 157 over 3. Or we could start just by multiplying everything by root 157. Let's just multiply the whole thing. And then put those numbers in the matrix. So make an augmented matrix. So if I multiply this by root 157, I'm going to have negative 3, 3, and then 3 over 13 times root 157. So get somebody to calculate that for me. Negative 3, 3, so we want 3/13 times root 157.
2.8915.
2.8915. So we could have kept this in radical form, but I think it's going to be a little bit easier if we just get rid of the radicals. Keep a couple of extra digits. And the constant term is going to be 200 times root 157. Oh, sorry, it's going to be negative 200 times root 157.
Negative 2,506.0.
Negative 2,506. 506. Okay. And then our second equation, the FZ, that's just going to be 12, or negative 12, and then negative 12 over 13 times root 157. Negative 11.566. Anybody else with that? Okay. And then we have 500 times root 157. 6265. All right, and then our last row is going to become 2, 2, 2, 2. Negative 4 over 13 times root 157.
3.8554.
Negative 3.8554. And that's going to be 0. So there's my augmented matrix. So, any strategy for solving?
Solve the first row, the third row, so that we can
Okay, so you want to multiply this row by 1/2 and then swap it with the so 1/2, and then we're going to swap. So that's going to give me 1, 1, negative 1.277, and 0. Negative 12, negative 12, negative 11.566, and 6265, and negative 3, 3, 2.8915, negative 2506. All right, next step. Right, so we have our leading one. We want to have zeros below the leading one. So we're going to go 12 times the first row, add to the second. We're going to go 3 times the first row, add to the third. This is good practice. Zero. 0. Like that.
negative 22.296.
Okay, and that's still going to be 6265. Right, and that's going to be 0, and that's going to be 6. And that's going to be negative something.
For, I don't think it's negative 22.296, I think it's negative 34.67.
It is, I made a mistake.
Okay, negative 34.
0.6934.
698. Okay, thank you.
Negative 2.8916.
2.8916, and this is still going to be negative 0.6. And the good news is we can stop working with the matrix here because we basically have the answer. We have one of the answers here, which I can then substitute in to get the other answer, and substitute in to get the other. So if we remember from our original equations, we entered them in the order of FGD, FGE, and FGF. So this one's going to give me FGF. FGF is going to be equal to 6265 divided by negative 34.698 equals
Negative 180.56.
negative 180 point. Okay, I'm out of room here, so I'm just going to call it negative 181, but keep the extra digits. Pounds. So that means that's compression. Okay, we can substitute that in here now and solve for FGE.
FGE and 0.4.
FGE? Anybody else get anything same or different? You got the same? Okay, so it was negative 505 pounds, which means that one's also in compression. And then FGD,
Negative 1.5.
so it's also in compression. So we got all three of them in compression. These two are in less compression than FGE, and that makes sense if you look at the way the horizontal force is pushing, but they are all actually in compression. All right. So we can highlight those now as being in compression. Right. So we're left with only the one force here that we're asked for that we haven't found. So we would move on now to do our method of joints at F. I'll skip to a new page. Okay, and let's copy the diagram onto the new page. Okay, so now we're going to do a free body diagram of F. Before we do our free body diagram of F, we need to figure out the directions of FD and FE. We already have these two directions. So the unit vector from F towards D Yep, that's exactly the same as the direction from C to A, which is probably easier to see. So that's moving 3 feet along the y-axis and 6 feet along the, oh no, sorry, 6 and 6. Yep, 6 and 6. Right. One of those is minus. We're moving in the negative y direction. Okay, and the unit vector from F to E is the same as the unit vector from C to B, which is, well, the unit vector isn't 6 feet. It's going to be just along the x-axis. It's going to be I hat. So if we do our free body diagram of F, we know FGF is compression, so it's going to be down. We're going to assume FC is in tension. And we're going to assume that these other two are in tension as well. So the one that we know here is FGF. And FGF was 180. And FGF the 180? 181 pounds. All right. All right, so I've got 3 unknowns. We'll write our equations of equilibrium. All right, so we've got the net force in the x direction equals 0. I'm going to have let me just copy that one over as well. Got it on the right page. Okay, so x components, I've got 3 vectors. So my 3 unknowns, or sorry, 2 knowns and 1 unknown. Three unknowns and 1 known. So it's going to be negative 4 over 13 times the 180.56 minus 4 over 13 times FCF. There we go. And then I'm going to have plus FEF, which is straight along the x-axis, and plus 1 over root 2 FDF. Okay, so I've got all 3 of my unknowns in there. That's not going to be easy to solve. Okay, y equals 0. So my y components are going to be 3 over 13 times my 180.56 plus 3 over 13 FCF, and then minus 1 over root 2 FDF. Okay, so I only have 2 unknowns in this one, so that's getting better. Net Fz equals 0 equals negative 12 over 13. Oops. 180.56 minus 12 over 13 FCF. And what's my z component of the other 2? 0. So this one I can solve. Right. So it's going to be the same magnitude as the other one. £6 for 181 pounds compression. All right. Once I know that these 2 are the same, what's FDF going to be equal to? No. Remember, this one has a negative value, so it's going to be 0. And if that one's 0, then what's FEF going to be? 0. that drawing. Go back up to this one. So that means this one was also in compression. And both of these ended up being zero force members. And they were zero force members because they only had forces in the xy plane. So these two that are collinear are going to have to be collinear, and they have a z component. They're going to have to be equal. And if they're equal, then the other two both have to be zero.
Could you conclude that before doing calculations?
You could, but it's a little harder to picture than when we look at the planar trusses, when you can see the zero force members. The argument's a little bit more complicated because we have to think in three-dimensional space, and the fact that these two are in the same plane and these two are in the same line. That's not in that other plane.
Why would those numbers be put there?
Why would they be which?
Put there, like in that structure?
Okay, so that's a good question. Why would those members be put there? And there's two really good reasons. One is that maybe the material doesn't come in lengths long enough to run this whole thing. Right, this is going to be over 12 feet, so 15 feet. So if you're making it out of lumber or something, then that's going to be a longer piece of lumber. But the real reason, and especially because these members are in compression, is if we have long members in compression, they're going to tend to buckle, and they're going to buckle less if they're shorter members. This is basically a constraint here that's preventing buckling. If they were all under tension, then there'd be no advantage to having that member there. Under tension, buckling's impossible. Tension's just going to keep making the member straighter and straighter. If it's at all off straight when it's in compression, it's going to bow and fail. Not because of the strength of the material, just because of the geometry of the buckling. All right. So that was a pretty long example for a space truss, and it wasn't really that complicated of an example. We only did 2 truss points, or 2 joints. In your exam, I think I can speak for Jim as well, but in the final exam, you're not going to see a space truss. They take too long. You should know how to do them. It's basically the same as the planar trusses. You just have more equations of equilibrium. All right, so we're going to move on to frames and machines. These aren't necessarily going to be trusses, but they're going to be composed of two force members, the same as trusses, members that are under tension or compression, so that we can, by breaking the frame or the machine into pieces, analyze the internal forces. So we're going to use the method of sections and the method of joints for things that aren't necessarily trusses. So, frames support loads while machines contain moving parts and are used to transmit and alter the effective forces. For our purpose of our analysis in statics, we're going to treat a frame and a machine exactly the same. Both are typically composed of pin-connected multi-force members. So the forces acting at the joints and supports can be determined by applying equilibrium equations to each of the members. Basically breaking it down into more manageable sized pieces until we can solve the equilibrium equations. Basically, we need 3 unknowns for something that's acting in a plane, or 6 unknowns for something that's acting in 3 dimensions. Once the forces are known, members and connections can be designed to withstand these forces. So that's why we're doing this analysis. Once we figure out what the pin force is on a pruner, then we know how big the pin has to be, and what materials we need to select for the pin. Once we figure out the forces on a beam, then we know whether we can use a 2x6 for the beam, or whether we need to use a 2x12 or 3 2x6s, or whether we have to make a laminated beam. And that's actually part of the next chapter, where we look at the more internal forces in beams. But this is going to be related. So free body diagrams for the machines and frames. Disassemble the structure and show free body diagram of each part. Show all forces and couple moments acting on the part. Identify any two force members and represent their free body diagrams as two equal but opposite collinear forces. Where two parts contact, we use Newton's third law to show the reaction forces and moments that are equal and opposite. So here's a simple machine, and we want to determine the force P that's used to lift this weight, 600-pound stone, and we also want to figure out the force on B. And B, the pin at B holds this pulley, and it also holds the fixed end of the rope. All right, so what should we draw a free body diagram of first for this problem? We're definitely going to need a free body diagram of B, so we could draw that. You just want to do the point at B, or the pin and the pulley? Yeah. Okay, so there's our pulley. They don't give us the radius, so it must not be important. There's my point B. What forces are acting on B? Okay, so I've got a force of tension down here. Oops. Just call that T for now.
Normal force
Normal force where?
on the pin.
On the pin. Okay, so what direction is the normal force going to be? Let's draw the other forces first. Then I'll ask you again. Okay, so we've got this tension force here. What else have we got? Right, so we've got this force acting at an angle of 30 degrees. It's going to be the same tension force. So whether I call it T or P doesn't really matter. Okay, what else? So here we've got another tension force. It's the same rope, so it's the same tension. All the frictions are pulleyless. All the pulleys are frictionless. All right, that's not it, because that's not going to be in equilibrium. Right, so there is a normal force at the pin, but since the pin is round, I don't really know the direction of that force. So it's a pin force. It's going to have potentially two components. So we would draw those in, call that one By, and call that one Bx. Okay, how many unknowns do I have? 3. Okay. How many equations of equilibrium am I going to have? Well, I could have 3 equations of equilibrium, but when I look at the moments, it's not going to be useful. Because all of the forces go through the center point except for these two, and these two are the same distance either side of the center point. So I'm going to need to move on to a different point. Let's write the equations of equilibrium, but we'll have to leave them to solve after we've done another part of the machine. So net force X equals 0. What forces are acting in the X direction? Vx. Okay, so that's 2 of my unknowns. Net force in the y direction is going to be By minus 2t minus t cos 30. That's another 2 of the unknowns. Can't solve. So we're going to need to move on. What part of the machine should we look at next? Alright, so if we draw a free body diagram of the pulley at D, what forces are acting on it? Right, so these are the same tension forces that we drew from the other pulley, but these ones are going up instead of down because they're at the other end of the tension member. And what else have we got? And we've got 600 pounds that's pulling down on the center pin of the pulley from the weight. Alright, so if we write, how many equations of equilibrium do we have for this pulley? We only have 1, but we only have 1 unknown, so that's okay. So net force in the y direction equals 0 equals 2t minus 600 pounds. So t equals 300 pounds. So if t equals 300 pounds, then we can go up and solve for Bx, which is going to be 300 pounds t sine 30 degrees, 150. And By, which is going to be equal to t times 2 plus cos 30 degrees. $860 pounds. So you're asked for the force P and the force on pin B if the weight of the stone is 600 pounds. So we've done that, except that we have the force B as a Cartesian vector. It'd be interesting to know what the magnitude of that vector is so we can make sure that the pin is strong enough. So the reaction at B would be the square root bx squared plus by squared so 873 pounds. So you'd want to make sure that pin was able to withstand something considerably larger than 900 pounds. A machine like that, you'd probably want to use a safety factor of at least 5, because you know people are going to abuse it, and also we're solving for equilibrium. We're not solving for putting the tension on there to lift it in the first place. So yeah, you'd want a safety factor of probably 5. All right.
What's the safety factor of time?
Oh, 5 times the design load would be the strength that you'd want to design for. And machines that are used in industry and on farms, like people still break them with safety factor of 10. So to keep that in mind. All right. So we'll continue this on Thursday.